Hello again everybody, welcome all. The workshop had turned into even more of a high entropy zone than it usually is, with all the last minute panics of trying to get the bike ready for Thunder Sprint, which really was absolutely a fabulous weekend, even with all the mud and the wet. Riding in the wet is actually something I almost enjoy, mainly because other people don't, so I can appear to be going considerably faster, though there were some very good people out there in the wet who were far better than I am. Anyway, I had some concerns about the bike, so I've done a little bit of a tear down, and I'll give you a little look at some of the things I've found. And I and Tom Lipton and a few other people have been trying to help Steve, Buckrun 11, sort out the issues he's having with threading on his Grizzly lathe. Now, he's cutting perfectly reasonable imperial threads, but only if he leaves the half nuts engaged and doesn't rely on the threading dial. And the threading dial does appear to be what's at issue. It's got a very strange behaviour. Initially he thought it was down to the fact that it was fitted with a 15 tooth gear rather than a 16, which wasn't appropriate for his imperial lead screw. But that hasn't cured it, apparently. And I've got some things I'll film on my lathe showing how I would check things out a bit. Now, some people who were commenting on Steve's problems were questioning whether he was set up for metric threading with translation gears or not, and one or two people had looked at his gear setup and said that he was set up for metric. He's not. At a glance I could tell that there was no compounding in the gears, and I get the impression that some people are not getting how the gearing works, and I'm just going to go through something quickly on the whiteboard, which I've temporarily set up to talk about simplex gearing and compounded gearing, and where the differences lie, and the impact of idler gears. So let's rearrange the camera and take a look at that. Now, hopefully this you can all see this okay. I've had to put the camera a fair way back to get this framed okay. So at the top here I've drawn a couple of circles to represent gears, driver gear and a driven gear, and I've drawn them at the side to show simple or simplex gearing, and I've got arrows showing the direction of rotation. And you know, anybody's going to be able to see 20 tooth gear driving a 20 tooth gear ratio is 20 to 20, equivalent to 1 to 1. Below it I've drawn again a driver gear and a driven gear, and I've drawn a couple of different idler gears of widely varying sizes. Now, one way of thinking about gearing is this is a 20 tooth gear. If it makes one revolution, it has moved by 20 teeth. So in the case of this small gear, let's just say it's a 10 tooth gear. If it's moved 20 teeth, it's moved 2 revolutions. When it drives the output gear, it's moved 20 teeth, so it moves this gear 20 teeth, that's moved 1 rotation. That moved 1 rotation, the gearing is still 1 to 1. This gear, it's moved by 20 teeth for 1 revolution of this gear, so this gear moves 20 teeth, 1 revolution, 1 to 1 gearing. The idler has no effect whatsoever on the ratio between these two gears. What it has done is changed the direction of rotation. Obviously, if there were another idler gear driving as well, we'd be back to this relationship of rotations. But again, the second idler gear wouldn't have affected the gearing. Okay, excuse my poor sketching skills. But now we have compounded gearing. This is our initial driven gear, which is driving this gear. And that's on a common shaft with another driving gear driving another driven gear. So now we've got two ratios to deal with. So I've just written some fairly arbitrary numbers in there. So to start off with, we've got 20 to 40, and in terms of revolutions, that's 2 revolutions to 1. And then we've got 20 to 80, again in terms of revolutions, is 4 to 1. And these multiply so that we end up with an overall ratio of 8 to 1 on the reduction. And this is where, when we're thread cutting, we might have the 127 tooth gear, which gives us our perfect metric conversion, being half of 254, and there being 25.4 millimeters to an inch. In fact, that's how the inch is defined these days. Now I think what Steve's got on his machine is, from memory, a setup like this. You've got a gear on the spindle which drives a pair of gears on a common shaft, and then there is an output gear driving, well, it's driving into a screw cutting gearbox, but ultimately into the lead screw. So this would be a 100 tooth gear, and this would be 127. So when he's set up for imperial threads, this is just an idler gear. It has no effect on the gearing between these two, and I think these are both 40s. Now what you do for, if you want to cut metric threads, is you move the gear over and you put a spacer in here. So now we have compounded gearing. So let's go and have a look at the behaviour of the threading dial on my lathe. Okay, I think I've just about managed to get everything in shot. I've got my my threading dial pulls forward to engage, and we are on the number 1 mark. I've got a line drawn on the screw and the gearbox just to give us a bit of a reference, and I'll zero the Z-axis on the DRO, and I'm rotating the lead screw down at the bearing support end. So if I rotate by one full turn of the lead screw, well, basically it's 250 thou, a quarter of an inch, which makes sense since I can measure the lead screw. So starting at the edge of one crest, one full turn, 2, 3, 4 full rotations, 1 inch. So it's a 4 TPI lead screw. So you could easily put a dial gauge on the bed and measure the movement, rotate the lead screw 1 full turn. Obviously if you do it a larger number of turns, the accuracy improves. So that's the first test. That's confirming our lead screw pitch. Okay, having confirmed that our lead screw pitch really is what we think it is. Let's see if we can frame this slightly better. Again, we've got our index marks on the lead screw. I've got my threading dial engaged on number 1. So if I now rotate the lead screw 1 turn, we're halfway between a pair of marks, come up to 2, and we're at a full mark, another 2, back to a number. So if I go 4 turns, 4 turns, and at every point that we weren't being buzzed by a huge fly, when these marks lined up, we were either on a line or halfway between 2 lines. So the threading dial is agreeing with the lead screw. And of course the other thing we can do is use the DRO, and if I move the saddle 1 line, I'm coming up with ½ inch, 2 lines 1 inch, 3 lines 1.5 inches, 4 lines 2 inches, 5 lines 2.5, 6 lines 3 inches, 7 lines 3.5. Final line, we've moved 4 inches. So the ratio here, there's absolutely no problem. I'm beginning to wonder if there isn't something very strange on Steve's machine, that if this ratio checks out and he's still having this engagement problem, I wonder if someone at some stage or at the factory, given that it had apparently had the wrong gear on the threading dial, hasn't actually fitted a pair of metric half nuts that are partially engaging with the lead screw and well enough to successfully cut threads. But it's the reason that the points at which it wants to engage are not agreeing with anything. So if you do this check, Steve, we can at least eliminate the threading dial as the actual source of the problem. I almost forgot to include this in the video, but this is an excellent book for those of you trying to get started in threading. It's part of the workshop practice series, which is a British series of books, but is pretty readily available in the US. I'm pretty sure Amazon carry it, and you can find it on eBay and a few other places. But this really is fairly comprehensive, covers cutting, metric threads on imperial lead screws and imperial threads on metric lead screws, and ways of working out gearing, working out alternative sets of gears that you can use, suggestions for what are acceptable lead errors. You know, if you're only cutting a short thread, it doesn't matter if the pitch is off by a couple of thou over 4 inches, you're still going to make a usable fastener, though not an acceptable lead screw. So I'd really recommend getting hold of a copy of this or borrowing a copy of this. Well, I've done a post-meeting teardown on the Settebello, and despite the fact that it ran really pretty well, it's rather a mechanical disaster, and I'm afraid I am not at all impressed by the person who put this engine together. The compression seemed to be pretty low, so I went to check the valve clearances and there weren't any. Now, that could easily be a case of this engine hasn't had much running time. I didn't in fact check them before the meeting, they'd been checked on a previous outing. But I decided to, you know, take a proper look, see what was going on. And when I'd got the cylinder head off, what was immediately obvious is that we've had valve to piston contact. Not so bad on the exhaust, but pretty heavy on the inlet. Holding the cylinder head up to the light and looking down the exhaust port, which is reasonably short, I can see we've got a slightly bent valve. The inlet I'm not sure about. Now, I got the cylinder head down here. These are some special head bolts that they hold the head down onto the barrel, and then the valve gear, which is sitting over there, sits on top of these. Now, I'm not sure it's because there are some copper washers down the bottom of all these holes that vary in thickness, or whether these aren't made accurately, or whether the holes aren't the right depths, but there was a completely random assortment of shims under the rocker gear to get it sitting level, which is an arrangement I'm not that keen on. Getting a manual for these bikes is very difficult, because quite often there wasn't really anything produced when they were new. You were kind of expected to be able to look at stuff and understand how it works and judge torque wrench settings from the size of fasteners. But I started noticing other things. The wire thickness on the two valve outer springs is different. The stems are different lengths, and obviously have the keeper in different place. There's a lash cap on this one. The inner springs, one of them is wound opposite for an interference fit. This one, they're both the same hand helix, so I've got a lot of investigation and thinking and reworking to do You can see that there's a plate under the barrel. The barrel has in fact been shortened by one fin, and the spigot machined on the top, and there's a recess in the bottom of the barrel, whereas the original setup, here's an unmodified barrel, would have been flat on the top. I mean, this engine has been taken out from 61 to 64 millimeters to get it close to 200. Now there's some things that are reasonably well done, like the needle roller conversion on the valve gear carrier, but the shafts themselves don't look particularly hot, and I am singularly unimpressed with the crude grinding with no attempt to blend out any stress razors. And I don't know how close we can get in here and focus, but the tip of that that rocker and the shape of it, and likewise the other, I mean that's an even worse finish. I mean, that's supposedly this engine was put together by a professional. Well, he may have been paid for his work, but I don't consider the actual attention to detail and the fit and finish to be at all professional. So we'll have to see what we can do. I mean, some of these parts, getting replacement rockers is going to be a case of finding an Italian speaker to do a bit of hunting around in Italy for me. Though possibly some of this may be available from America, seeing as Herdan are still around and have some old stock. Anyway, a few bits and pieces to do. Hopefully it'll get sorted out and we can have it back on track on July the 4th, for the Morini Riders Club track day. Because, you know, it went reasonably well, and with all that's wrong with it, it has the potential to be an awful lot faster, which could make it quite a competitive machine.